All right. Hey, everyone. Ooh, all right. Awesome. That sounds great from up here. This is the longest title I've ever made in a presentation. And I will spend the next 5 minutes reading it to you. So, designing better games using artificial intelligence, automated playtesting, and computational creativity. Before I get started, I'm going to talk about what I used to do. So I was a game developer for a long time. I started making games in 2003, making them for those flip phones we used to have with buttons on them. So a game called Armadillo Gold Rush, which was a really big hit in Venezuela, strangely enough. And then I made an iOS game back when people hated free-to-play games. I was one of the pioneers to get all that hatred. So Chip Chain was a pretty successful free-to-play game. I also helped found Indie Fund, which has helped fund a bunch of really great indie games, I think over 30 by now. I'm the chairman of IndieBox, which makes actual boxed indie games. You can get them delivered to your house every month, and there's manuals and like physical stuff. It's really amazing. I'm advisor for Fig, which is a new way of making or funding games. So it's a little bit like Kickstarter, but you can actually invest in the games. And I've done a lot of work with Indiecade. I've helped run Indiecade East. And now I am getting a PhD at NYU because I'm not busy enough. I'm going to talk to you about some of the really cool stuff that's going on in academia and how it can help, I think, make better games. I think developers spend a lot of time kind of making things that are very similar to what already exists. And I'm really interested in finding new ways of getting inspired to come up with new ideas. So let's talk a little bit about artificial intelligence in games and how it's used. So most of the time, we get things like this, which you use artificial intelligence to build basically speedrunners, right? They're like these amazing feats of inhuman ability that the computer looks forward in the future. It figures out in the next half a second, what's the best thing I can do? What crazy buttons can I push in order to be amazing? And it helps do some really cool stuff, like this is Cloudberry Kingdom. So this game, it generates levels for you of different levels of difficulty. So there's the easy one. This one I probably couldn't even do. You get this guy. And it gets worse, yeah. So, I mean, obviously people are not doing that, right? I mean, there's probably somebody in here who can pull that off, but, so anyway, computers can do really smart things. They can be better than people. Something else that is done a lot with computers is using neural networks to learn how to play. So here's an example of this bot that knew nothing, and it's learning to play Super Mario Brothers. And this is, 20 generations in, and it's learned to jump a lot. It died in that pit, but it died. Okay, so now it's going to learn, I see a pit, I need to do something different. So that time it survived. So we'll come back to neural nets. That's a pretty cool thing. Artificial intelligence has been used in the Talos principle. Every time they do a check-in, so they change the level, they check it in, this bot goes and automatically plays the game, and it verifies that the people who made the check-in didn't break anything. So these bots don't actually solve puzzles, but they do know how to solve each of the puzzles that's in the game, and they can make sure that the game still works. And so I think it says there are 15,000 hours of playtesting. Procedural content generation is pretty popular. I'm sure everyone knows about this now. I mean, it got started in Rogue in the 80s, making the maps, and then Dwarf Fortress is kind of the extreme case of that, where it's evolving weather systems and erosion and entire histories of species and everything. Spelunky with our host there, wearing the blue hat. And Binding of Isaac. I mean, these are all really popular examples of how PCG is used to design levels and make the game, replayable over and over again. I first used procedural content generation in our game Armadillo Gold Rush this song here. Let's play this. So this was actually written by a computer. So I don't play banjo, I play drums, but I don't know if you can hear it. Is that loud enough? Close enough. It's pretty cool. It's got picking, it's got bass lines, it's got the washboard drums, all this stuff. And so, that's right, I'm gonna stop it. So, yeah, computers can create, other content besides just the levels. They can also create music, they can create art, they can create rules for your game. Here's an example of a board game that was designed by a computer. So it has this really cool feature where so the object of the game is to get 4 pieces in a row. Okay, lots of games do that. But in this game, if you get 3 in a row, then you lose. And so the object is to force your opponent to have to block your 4 in a row by putting a piece down. So you can see that's happening in the upper left. There's like 1, anyway. Black has lost this because there's 3 black pieces. So a computer, this was made by someone named Cameron Brown, and this game took a bunch of different rules of all these different games, it combined them in different ways using genetic algorithm, and spit out this. This rule has never been invented by people. So this rule, the idea of dying if you make 3, but winning if you make 4, was invented by a machine. It's actually a publishable game. You can buy this. So what other ways can we use AI to help us make better games and be inspired? Here is the process that I'm doing in my PhD. So we're looking at iterative game design. So you start with some rules and some parameters for your game. That gives you a new variant of your game, and then you play test it either by yourself or with some people. You interpret the results that come back, and then you make some adjustments to your game. Okay, and so each time you go around this loop, you get a different version, and finally you get to a point where you're happy with it. And what I'm going to do is use this to have a computer do each of these things. So the computer is going to set the rules and the parameters, the computer is going to play test it, and the computer is going to interpret the results of the playtest. And I'm going to do this in the framework of Flappy Bird. So I'm actually getting a PhD writing clones of Flappy Bird. It's pretty ridiculous. But anyway, so here are different versions of Flappy Bird, right? We have different distance between the top pipe and the bottom pipe. The pipes are different distance apart. The width of the pipe, we also can adjust gravity. We can adjust the size of the bird, how strong it jumps, how fast it moves. And we let the computer play it and say, okay, well, which of these are easier and harder? And in the beginning, if you just make one of those superhuman computers, they can play Flappy Bird perfectly. So it goes through this whole level and it never crashes. And we don't learn anything about it, other than we know at least it's beatable by somebody. If you made this pipe gap really small, then that game wouldn't be playable even by the perfect computer, because as you jump through the gap, it's not big enough. So some of those games are impossible for everyone to play. And the way we do this is actually something that all of us can do. This is not really that complicated, but you basically look forward in the future and you figure out when you want to make a jump. Okay, so that's pretty easy. You just simulate your game forward until you realize, okay, it's time to jump. You record how much time that was in the future. So let's say it's 600 milliseconds. And then we adjust the amount of time. So instead of saying 600, I'll say, oh, sometimes I'll do 580, or sometimes I'll do 620. You just make a little random adjustment. And if that number is too early, then you crash into the top pipe. And if it's too late, then you crash into the bottom pipe. And you can simulate a really experienced player by making that random jitter a small number. And if you can simulate a novice player by making that number really large. And so if the distance or the change in time is really large, then it's like people are making lots of mistakes. And this is great because when you're designing your own game, you often forget what it's like to be a beginner. You've gotten better at it, and you no longer know what it's like to be a novice. So this system here can play as a novice, or it can play as an expert that's even better than you. And so this is what the game looks like when it's being played by the computer. So on the top, that game is harder than the game on the bottom. And we can tell that because on the top, none of the Flappy Bird players are making it to the end of the screen, whereas on the bottom, a lot of them are making it off. And this takes I don't know, you can do this 100,000 times in a second or something. It's super fast. So you get really quick feedback on how difficult your game is. So I said, okay, well, what happens if I try all sorts of different gravity and all sorts of different jump? Right? So this is like a graph of every dot here is a different Flappy Bird game. We simulate thousands of times. And the large dots are the Flappy Birds that are pretty easy to play, and the tiny dots are the ones that are really hard. And if there's no dots, the game's impossible. So like in the upper left, you have really strong gravity and a really weak jump, so you just smash into the floor. every time you play it. And on the bottom right, you have impossible games because there the jump velocity is so high that you smash into the ceiling as soon as you jump once. And in between, you have kind of a range that the game actually works. And then towards the upper right, those games are easier because, harder because it's like really frantic. Like gravity's pulling you down really quick and jumps moving you up really quick. And Flappy Bird is like somewhere you can see it's indicated there. So one of the things you can do is you can say, okay, computer, go find me a game of a certain difficulty. Like I want 20% of people to die on the first pipe. And this is what that looks like. You use something that's called like a optimizer, and this is something you just like get a little package off the shelf, and you say, okay, go ahead and go look for one. So it adjusts the parameters for you, and this is an example of how it looks for that game of that difficulty. The X's are the ones that are impossible. And the dots are, again, the closer it is red here, the closer it is to the target you're looking for. So I'm going to show you what this looks like when we run it. There's lots of Flappy Birds. So let's make gravity a lot stronger on these poor little guys. They're all smashing into the floor. Aww. Or we can make gravity really weak. They're going to fly up into the sky. All right, but somewhere in between, we're going to find some nice. All right, let's restart that. We can, make it really random. Let's speed this up. It's taking too long. There we go. So what happens if we make them jump stronger, right? Too hard. Poor little guys. Aww. Anyway, so it's pretty fun. This is on the web. You can go out and you can play. It's a long URL, but we'll find a way to get it to you. Maybe we'll tweet it out later. This is a game that was generated by our system. So I said, okay, I want you to generate a new game for me. This is something I call Frisbee Bird. It's the same exact rules as Flappy Bird, but what's going on here is you have to tap really fast to get it to move up even a little bit. And then it kind of floats on its way down, and the bird was generated wide and kind of thin, so it actually looks like a Frisbee. This is an entirely new game generated by a computer. Well, not entirely new. I mean, it's certainly the same exact rules as Flappy Bird, but it has a very different feel to it, right? And so this is pretty inspiring to me when I see a computer tell me, hey, here's an interesting thing to check out. And then I can, as a designer, go through and go, all right, cool, this is awesome. I'm going to make that look a little better. I'm going to tweak the numbers to be a little more challenging, a little more fun. But at least the computer, gave me an idea. And so this is kind of the process that I think is of designing here. In the green area, those are like the games that are pretty close to your original idea. And you can make little small adjustments. And then if you make them too far, you get into the gray area. And those games are the terrible, crappy ones that are broken. But there might be something really interesting out there that's even further away on the frontier. And it's hard for us. We have a limited amount of time, and we have egos that get upset when we start making bad things that are not working very well. But the computer is just stupid, and it's brave, and it's willing to work all night on finding you interesting Flappy Bird clones. So it'll go out there and kind of find these unique ones. And so we can represent this sort of mathematically, and we can say, okay, find the games that are as far apart from each other as possible, that are still playable. And here are some of those versions it generated. This one is called Needle Gnat, and I'll show you what these look like in a second. But Needle Gnat, Lazy Blimp, was kind of ridiculous. Droppy Brick is like this game where it falls really quick, and Pogo Pigeon. You'll see why it's called that. Let's get back over here. All right, here is Frisbee Bird. We saw that earlier. That's nice. Okay, this is Needle Gnat, which is actually playable. It looks like it's really hard, but this game, the pipes are all the same height, so it's really a game about how accurately can you tap in a row. Here's that terrible blimp game that it generated. So I don't think anyone's ever going to want to play this, but it is inspiring to maybe try to make something like this. Droppy Brick is actually pretty good. It's about, like, can you deal with drops from really high to really low? And then Pogo is this guy. All right, so no human helped make those. Those are all computer. I think it's pretty interesting. Okay, what's beyond making Flappy Bird clones? Can we do something that's even more interesting than that? I think definitely yes. So I don't know if a lot of people here have seen Deep Dream, but this is a way of using neural networks to create new pictures. So you feed it an image, and you give it a neural network that's trained to recognize things in it. So like this neural network is called GoogleNet, and it's trained to determine what species of or breed of dog you gave it, and also flowers and like building types. And so then when you feed it an image, it looks around and it finds dog faces and buildings and trees and things in it. And here's a picture of my dog Trixie. She's very cute. And these neural networks are very complicated, and they have different layers in them. And the early layers do things like find edges or find circles or find like squares and things. And then as they build up, they find more complicated things. So what you can do is look at one layer of that neural network, and you can say, okay, I want you to do what you can, change this image so that you really like this image. But you don't tell it to the image of the neural network at the end, you tell it the one that's responsible for finding lines. And so here, it's gone through and it's tried to make that image as pretty as it can for itself, and it's found all sorts of pretty lines. And if you tell the network that's responsible for finding dog faces, right, then you get these nightmare images, right? My poor dog with the dog feet. And if you take that image and you put it back in to the deep dream, and you keep going through over and over again, and so it's like having a dream within a dream within a dream within a dream, you get the really terrible doggy face nightmare. But what does that mean for games, right? So what I would love to see is to take a neural network that's trained to play games, right? It's one of these things, it's learned how to play Mario Brothers, but then you adjust the level to make one of those layers in that neural network really happy with your game. So one of these layers is going to be responsible for jumping over pits. So if you tell that layer, hey, modify this level so that you like it, it's going to make a level with lots of pits in it. And part of this network is designed for avoiding monsters or stomping on them. And so it will make a level that's all about stomping on monsters. So, we can go and have this neural network, along with this dreaming, kind of dream up new levels for us. There's another related work called Neural Style, and you feed in an image, like here's the Golden Gate Bridge, and then you feed in a style image, and it creates new pictures with the original structure, but in the second picture's style. So I did a little experimenting with that, and here is a structure of Super Mario Brothers with the art style of Zelda. And so it's done this kind of neat thing where it's like, you can see it's used the mountains in Zelda in order as some of the texture for the blocks. It's turned Mario into like a fairy heart thing. I don't know. The cloud there has become a rock, and it's kind of neat. I mean, what else can we do with this? Here's the Mario castle crossed with a famous castle, and it creates like new level designs. So that's pretty interesting. Can definitely be inspiring, I think. I do think there are some concerns with using AI for this kind of stuff, so I want to spend the rest of my talk talking about that. We are writing a paper right now about what happens when you have superintelligence, which is when AIs can learn to improve themselves, and you just you plug them in and let them go, and they just keep learning and learning and learning. Eventually, they get smarter than people. And then you keep letting them go, and they might even get so smart that the relationship from the supercomputer to us is sort of like our relationship to a 2-year-old child or to an animal, or that an expert chess player is to a novice chess player. And so we wanted to ask, what kind of games will those superintelligences play with humans? And there might be games like Candyland, which is something we play with little kids, and it's not very fun for adults, but we do it because we like children, we want to make them happy. And so, basically the superintelligence computer is playing chess with us, and it's like, haha, it's so cute. I know that white can win every time I play, and I'm just going to humor you and let you think that you're learning. But it's doing that because maybe it wants to entertain us or make us happy. There are some games that humans play, which aren't so great if it happen, and we call these domination games. So like rodeo, bullfighting, hunting, and fishing are examples of these things where if the superintelligences are a million times smarter than humans and they need a better battery and we've got a bunch of atoms, they might be like, you guys are kind of dumb. You're not going to do much left, so let's just turn you into a battery. So these are some of these concepts we want to start, at least thinking about to be prepared for when this happens. And a lot of this stuff I've talked about, or if it happens, a lot of the stuff that I've talked about was about how to be inspired and how to design games automatically. And I think it does ask the question, am I trying to replace the job of a game designer, right? And that's definitely not what we're interested in doing here. What we really want to do is make tools that help make the job of a game designer easier, better, faster, more interesting. And so we want to kind of gear things towards like these tools that can inspire us and help us do new things and make the game industry something that is very exciting for the next 20, 30, the rest of our lives for sure. All right? So thank you very much. I have time, looks like, for questions. So yeah, thanks. All right.
Perfect, we got questions already.
How do you create a reward system for the AI? Like, why does the AI care if it falls in a pit or not?
In that example, the reward is how far does the get. So it's basically like you can do score, or you could do like how close are you to the goal flag. But it's up to the user to decide what the reward is. Yeah, the AI wants to maximize score, for example. Yeah.
About halfway through the talk, you mentioned something about an off-the-shelf optimizer, and I'm wondering what that is and what the role of that was.
Yeah, when I said off-the-shelf, it was not the right word, but you can basically download, there's like so many different packages out there, and you might need a little help like translating it into, it'll be written in C, it'll be written in Python, it'll be written in Java, it'll be written in Lua. Like all these researchers will try to make it as easy as possible to use them. And they're basically like little one-function things you plug in, and you say like, here's the thing you want to maximize, like score. Here's a little function that'll tell you what the score is, and then it goes around and tweaks all the numbers for you. You don't have to like develop that yourself. In fact, I've never done it.
Are they like constraint solvers, or?
Yeah, something like that, yeah.
Ignoring kind of the dystopian future you talked about where they're going to kill us all,
Yeah.
do you think computers are going to reach a point where they can make games that rival what we're making now with kind of the human elements and the creativity factors?
Yeah, I think that Yavalath was that game, that abstract game I showed you with the red, black, and white tiles. That game is, you can buy it. Like it's a total legitimate game. So I do think that computers are making games that are as interesting as what human designers can do.
How many activation layers are there in these networks, in the neural networks, on average?
For the Mario one?
For the image one that you were showing.
I don't know. I think it's like 17 or 19 or something like that. Those things, you just download them. You don't make them yourselves. It's like, people at universities and Google are paid to just sit there and try to tweak all those complicated networks, and then they just give you the network. And then you use that to make the images. But in the sense of the Mario, that neural network is actually created on the fly. Like, it's using a technology called NEAT, which is, it just tries different neurons and different connections, and then you just run it overnight, and it comes back and says, here, I've learned how to play.
Just kind of the follow-up what I asked before. Like, I understand that computers can make games that are smart and creative and things like that in sets of rules, but do you think computers will be able to make games that have like the sort of human emotional appeal to them, or any kind of things like that beyond just creating a solid kind of structure?
What they do is that computers are good at doing what they're told. So if you tell the computer, here's the properties that make a good game, it's got to, be a game where you're not sure who wins until close to the end. It's got to be a game where the more skill you have, the better you do. So in that Yavalath game, it wasn't just like, hey, computer, go on your own and come up with things. He had like 70 different metrics that decide what makes a good game. And he determined those based on actually looking at real games like chess and checkers and Othello and those things. So if you know how to tell a computer what a good narrative is, then it could create good narratives. But no one today knows how to write a formula that says this is a good narrative. That's still in the domain of us to do. That's really the challenge. It's easy to say maximize a score. It's hard to say, make me feel the difficulty of losing something that's important to you. Like, that's not easy to write a program to do.
I, for one, welcome our new game design overlord.
Yeah.
Robotic ones.
All right, so...
It's like a perfect last question, I think, unless Colin has one. But I don't know if you can do any better than that.
Well,
what?
we have time for a couple more questions.
Oh,
I have a couple of questions.
Yeah.
So, considering I haven't done, I'm a game designer, I write games, I'm an indie game developer, and I think this is really interesting, and I'd like to start working on it. What's like my on-ramp? Like, where should I start?
To do which
Yeah, so like, I'm working on a game, say, and I want to explore things, and I want to explore territory that it's hard for me to do as a person, and I want to start using a computer to do it.
Yeah.
How should I start?
Well, I think actually one of the easiest ways to start, if you go to my webpage for the Flappy Bird thing, it's written in JavaScript. So, you can just look at the code for it, and you can see exactly what we do there to kind of adjust the time in the future in order to make it jump. I think that might be a way to kind of see, oh, okay, I can do this. There's also a lot of academic papers that are out there that they might be a little bit challenging to read in the beginning, but I'd be definitely happy to point people to it. You can reach me on Twitter or email. They have done lots of different ways of kind of making this work and showing how AIs can be used for this sort of stuff. So it's not as complicated as it sounds. It's a lot of this stuff is really hacks that people are writing really complicated papers around, but they actually ultimately are just pretty simple things that they're trying.
And then kind of an airy-fairy question. Do you think there are going to be weird questions about authorship? Like who actually invented a game?
So Michael Cook has made a program called Angelina, and when Angelina can design arcade action games, and he attributes the generation of the game to Angelina. I personally would attribute it to the person who made the software, but I think what's most common for people who are in this field is that they attribute it to both the person who created the software and the software that created it.
All right.
Thank you.
All right, perfect. Thank you very much, Aaron.